The introduction to inverse functions. So for the table A, what you had to do is you had to take all of these input values x and plug them into this function y and get their output values. And when you do that, you get -8, -1, 0, 1, and 8. Because essentially what I'm doing is saying -2 to the third, -1 to the third, 0 to the third, and 1 to the third. And the only thing to remember is that when you take a negative number to an odd exponent, it stays a negative number. Okay, so then what you needed to do in table B was plug in -8 to this function right here. So the cube root of -8 is -2. The cube root of -1 is -1. 0, you get 0. Cube root of 1 is 1. Cube root of 8 is 2. So if you notice, the relationship between tables A and B is that the values are switched. So since they're switched, what this means is that the functions given undo one another. Therefore, they are inverses. So the notation f of -1 represents the inverse of the function. It's not the reciprocal of f, the function. So if you have x to the third, then f to the -1, the inverse of f of x, is going to be x to the 1/3. So it's not 1 over x to the third, it's x to the 1/3. So just make sure that you note inverse and not reciprocal. So now I'm going to take the values from table A and table B and plot them and graph those two functions below. And I'm actually going to change the scale and count by 2 so that we can fit 2, -8, 2, 8 and the 8, 2, and so on. Okay, so here are the values from table A in purple, and the points from table B are graphed in green. Okay, so it also asks you to plot the y equals x line. So that's going to look like this. And I'm going to do it as a dotted line so you know it's just something to look at. It's not an actual function we're plotting. So y equal x goes through 1, 1, 2, 2, -1, -1, -3, -3, and so on. Okay, so there's that line. So it wants you to describe the relationship you observe graphically. So what do you notice? Well, I notice that both functions reflect onto each other over the line that we wrote y equals x. So if I took the purple line and I reflected it over y equals x, it would be on this part of the green line. And that goes for every other part of the two functions that we graphed. So in table C, if I take all those x values on the left and I plug them into the function h, which is 2 to the x, these are the following values that I would get for my output values. 1/4, 1/2, 1, 2, 4, 8, and 16. So, knowing that these two are inverses of one another, because over here it says y is the inverse of h, then based off of what we just completed before and what your textbook says, the x and y values are going to switch. So, for the inverse of h, whatever that is, if I plug in 1/4, according to the table over here, I'm going to get out -2. If I plug in 1/2, I'm going to get an output of -1, 0, 1, 2, 3, and 4. So again, when I plot these, I'm going to count by 2 on my axes, and I'm also going to graph the line y equals x. So the values from table C are graphed in blue, and the points from table D are graphed in red. So again, when I graph my y equals x line, the relationship that we observe is that another reflection over y equals x. So, looking at this one, what are the domain and range of h, and what are the domain and range of the inverse of h? So, the domain of h, which I'm going to write over here since I don't have room, the domain of h is going to be all round numbers, or negative infinity to infinity. The range is going to be 0 to infinity, because these are exponential functions, and it's never going to cross the y-axis. So since that's the case, notice how I have parentheses around 0 instead of a bracket. So when you look at the inverse in red, the domain is going to be 0 to infinity because it's never going to cross the y-axis, which is a parenthesis, and the range is all round numbers, so it's negative infinity to infinity. So it asks, describes the relationship between the domain and ranges of the inverse functions and explain why this relationship must always hold. Well, think about it. If we take the values, the input values and output values, and switch them to get the input values and output values of our inverse function, then the same thing's going to happen with domain and range, because the input represents the domain and the output values represent the range. So if we switch them, the domain and range also get switched as well. So in this next problem, it's a given function, g of x, and also graphed is the y equals x line. So they want you to sketch the inverse of this given function and then describe the process of how you did that. So this is what I'm going to do first. This is my process. So this is what you can write right over here. I'm going to identify the coordinate points of all of these corners or endpoints, if you will. So over here to the all the way on the left, this is -6, -2. At this corner up here, we have 0, 3. And then over here, all the way to the right, this endpoint is 7, 6. So since we just realized in our table that the input and output values switch places, then I know that the new coordinate points of my inverse are going to be the opposite or switched x and y's of the given function's values in red. So essentially what I'm going to do then is I'm going to take this -6 and -2, and since they switch places, I'm going to graph -2, -6. And I just want to write that down over here so you know where I got that from. So I'm going to go to -2 and down to 6, and I have my point all the way down here. And then I'm going to have 3, 0, which is right here. And then I'm going to have 6, 7, which is all the way up here. So I don't have a ruler, so hopefully I can do this sort of straight. This is the inverse, which, if you notice, is the reflection of the original function over the y equals x line. So looking at that function and its inverse, we're going to identify the domain and range. So the domain of the original function, all the way to the left, I have -6, and since that value is included, I'm going to use a bracket. And all the way to the right, my x value is 7. Again, it's included, so I'm going to use a bracket. Its range, the lowest value is -2, included. And the highest y value of that original function is 6, included. So what I'm going to do is I'm going to switch them. I'm going to write 7, -6 before I even look at the graph. So now I'm going to look up and notice, okay, is the farthest left value for my domain domain, excuse me. I'm sorry, I didn't do this correctly. I don't want to switch those values. I want to write the range here, so it should be -2, 6. All right, sorry about that. So if I look at my inverse function, the farthest left point is -2, and the farthest right x value is 6. So then, if I copy down the domain here, -6, 7, is that the lowest and highest values of my inverse? And it is. Okay, so after you read through those pages on one-to-one function, if each element from the range of a function corresponds to only one element of the domain, this function is said to be one-to-one. What test is used to determine this? This is the horizontal line test. And then how does this work? It works very similar to the vertical line test. So if the horizontal line only crosses the function, then I'm going to abbreviate, at one place, or let's add at only one place, that means the function is one-to-one. Okay, so let's analyze the functions g, h, and k. So here they are in table form. So for each of the functions, decide if it has an inverse and why or why not. Okay, so g of x, does it have an inverse? Yes, it does. And I'm going to tell you why and not write it so it won't take too much time. It does because every y value has only one x value. Now, looking at h, does this have an inverse? No, it doesn't. Why? Because you can't have the function h have an output of 6 because that 6 value is linked to x equals -1 and +1. So essentially, that point 6, -1 and 6, 1 would fail the horizontal line test. And the last one, does k have an inverse? Yes, it does. Once again, every y value has only one x value. So looking above at g, I want to do the inverse of g. So I'm going to have my output values now become input values. So I'm going to have an input value of -2.5, 0, 2.5, 5, and 7.5. And those corresponding output values are -5, 0, 5, 10, and 15. And I got those because those were the input values of the original function g. So now looking at h, well, this is an issue. We just said it doesn't have an inverse, so I can't make this table because the inverse does not exist. So it can't be done. And lastly, k is going to have your input values are now -1, 0, 1, 2, 3, and those output values are going to be 1/3, 1, 3, 9, and 27. And the last part of this is just evaluating the functions at the given input value. So g is the table that you don't see here that you have above you. So g of 5 is 2.5. H is also in the tables above, and at -1, h is 6. And k above at 3 is an output value of 1. So then if we look at some of the inverse problems and notice there is no h, so we're only looking at g and k. At 5, my output value is now 10, and at the inverse of k at 3, you now have 27.